So, hello everyone, good morning. So welcome to the seminar. Today we have the pleasure to have Professor Yezzi from Georgia Tech Institute. And Professor Yezzi right now is the Junior Hightower Chair Professor in the School of ECE. And Professor Yezzi got a Ph.D. from the University of Minnesota and also did the postdoc at MIT. And Professor Yezzi's research interest is mainly in, definitely you will see today, is mathematically sound framework and mathematically sound method to handle a wide range of image processing computer vision applications, and which is not very often nowadays you see in deep learning, people tune parameters without a mathematically sound understanding of the framework. So that means it's a good opportunity. We can learn more and see more excellent work from Professor Yezzi. So without further introducing, so let's welcome Dr. Yezzi.
Thank you very much. So today I'm going to begin the talk by just showing an applied research problem that I've been working on for a couple of years with some students in cardiac image processing. And we threw a whole bunch of sophisticated machinery from a modeling standpoint at the problem, and because it's a tough problem. And we would get close to getting reasonable results each time. It would get a little bit better, a little bit better, a little bit better. And then find that there was one little tweak that made the that suddenly made it work. And it still needed all the sophisticated modeling, and I'll show you that really quick. But without this little tiny tweak, it would either fail miserably or work beautifully. Right? And so the tweak seemed to us at the time a hack. It turns out to be a common method. We just didn't know about it. A common method people use all the time in machine learning to accelerate optimization processes. But then we want to try to understand a little bit more rigorously, and that kind of led to the work that I'm going to show you today. So let me, so basically what I want to talk about today at the end, after I introduce it with the application that got us interested in it, is many of you might be familiar with momentum-based gradient descent techniques, or sometimes they're called accelerated gradient descent techniques. And they actually go back quite a bit to Nesterov for optimization on convex problems, but they're used quite a bit for non-convex problems as well. And actually, they even go back before Nesterov to, I believe it was his Ph.D. advisor, Poljak, that put forth what are called heavy ball techniques. So they've been used a lot. And they're a major power horse in machine learning and in big data problems. But for the most part, they've been just treated in finite dimensions. And so what do you do in the infinite dimensional case? So there was some work that was done a little while ago to put these into the framework of ODEs in finite dimensions, and what we're going to talk about today is how to do this in the context of PDEs. So before I get started, I just want to mention that I do have some collaborators working with me on this. One is Ganesh Sundaramurthy, Jeff Calder, and then my PhD student, Minus Benjamin. All right, so let me talk just briefly about some of the work that got us interested in this. So I've done a lot of work in the area of active contours. So active contours are curves that deform the domain of an image, typically in 2D or 3D, and the goal is to get them to evolve towards the boundaries of an object of interest. So just to show a few examples, here's an active contour that's deformed to detect the fan bone in a chicken, like this is automatic food inspection during the processing. Here's an example of an active contour that's evolved to capture the boundaries of the ventricle in a cardiac ultrasound image. Here's an example, another medical imaging example of an active contour finding the boundary of the bone in a knee. And of course, you can do this in 3D as well. The techniques that I use a lot, and I'll show this at the end of the talks in the context of PDE acceleration, are level set methods. You can embed contours or surfaces as level sets of functions over the same Cartesian grid where your data is represented, and this allows you to not have to worry about coming up with a separate sampling of the curve and resampling it as it evolves. It also allows you to handle topological changes very naturally. Here's an example of a single contour that evolves and splits off into several contours. Here's an example. If you don't know where to initialize, you can use this topological flexibility to have this initialization strategy where you just seed the entire domain of your data set with separately connected contours, and you'll let them all evolve together and merge together. This is an OCT image of some tadpole skin cells. All right, so of course, you can do this all in 3D as well. Here's an example. This is a 2D cross-section of a confocal microscopy volume of dendrites in a rat brain. And so we start off with an initial surface, which is like a volumetric cube. It's actually more of a rectangular solid. And then it evolves and captures the object that you see here. So anyways, the point is, you can see with these examples that you can handle either very simple shapes or very complex shapes because you're not imposing some finite dimensional structure on the shape representation. Okay, so that's the generic active contrast. So now what if you want finite dimensional structure on the shape representation, but you don't have something simple like a bounding box or an ellipse that already has a nice analytic form for you? Well, you can do principal component analysis on that as well. So you get a whole bunch of example contours. Here's an example of some principal component analysis results from airplane images. Here's an example of PCA results from handwritten figure 4s. And again, you can do this in the level set framework. You come up with level set representations for all of these shapes. You align them. You subtract out the mean, then you do PCA on the result, and now you come up with a finite dimensional model that can also handle topological changes as well. So that's another kind of advantage that you get from this. So here's an example of PCA results on a plane. Here's the mean shape. Here's plus or minus 1 standard deviation in the first component, the second component, and the third. Okay, so you can do this as well. Now, all of this, none of this is the new stuff. This is just stuff that, historically I've done some work on. And I'm using all this stuff in a cardiac segmentation problem, which I'll show you now. So, of course, you can do PCA in 3D as well. So in myocardial segmentation, it's extremely challenging. There's reasonable success from various algorithms to segment out the boundary of the left ventricle, which is what you see here. So for now, just ignore the blue, gold, and red contours and look behind at the image. Because there's reasonable contrast. Now, it's much more challenging to segment out the right ventricle. These are CT images. So typically, these are contrast-enhanced CT images, and when they inject the dye, one of the chambers has good contrast and the other doesn't, right? It depends on how you time the acquisition. So, you can segment out one nicely, the other's harder. But what's almost always hard is trying to find the epicardial boundary, which is just, it's even hard for a human, right? So you have to be kind of trained clinician to find out where it is, because in some places you just know where it is because that's where it's supposed to be, and there's really no obvious visual feature there. So this is an example where using some kind of shape prior and some kind of machine learning, in this case we just use simple PCA, is useful. So we come up with a three-dimensional, finite dimensional model for these three different pieces of the myocardium. So the two inner boundaries for the left and the right ventricle, as well as the outer boundary for the epicardium. And we initialized just using the average from our training examples, and now we just evolve a finite dimensional, we solve a finite dimensional optimization problem. We want to fit this to the data using as our parameters pose, so we're allowed to translate, rotate, and scale these, as well as the shape parameters that we got from our PCA. So it's just, it's not incredibly small, but it's not a huge vector either of parameters that we optimize over. All right, so what are we optimizing? So we come up with a fitting cost, which is, as long as there's no overlap between those shapes, there's basically, it decomposes your volume into four regions, right? You have inside the left ventricle, inside the right ventricle, outside of everything, and then in between the two, which would be the actual myocardial muscle. So in these four regions here, left ventricle, right ventricle, myocardium, and background, we come up with a simple representation of the data as being piecewise constant. And in the background, since we have dark areas and bright areas, we have bone, and we have we fit it to two constants. So you can think of this as a two-level C-means representation where we match to two possible intensities, and then we take the minimum of the two. So that, of course, right there for the background makes the problem non-convex. If it weren't for that, this would be convex so far. But we're going to make it even more non-convex because we're going to make this subject to inequality constraints. So, we have a nice sophisticated training model for the shape, but this appearance model is pretty trivial. So to make it a little bit more biologically meaningful. So we know how the contrast is administered. We know that the left ventricle area, based on the timing, should be the brightest. Then the right ventricle blood pool should be the next brightest, and the myocardium should be the darker. And then in the background we have bone, which is very bright. That should be the brightest of all. And then everything else, where you just have fluid, will be very dark. So we impose this ordering between the constants that we're fitting to. If it weren't for that, we could simply say, okay, look, this is a convex optimization problem. Choose the constants to be the mean in every single region, and now evolve the shape. Okay. Now we're going to make it even more non-convex. We're going to also insist, because there's nothing built into our training that guarantees that our model doesn't allow these three different boundaries to not overlap each other. So we want to make sure that they stay non-overlapping. So we incorporate that as a penalty in the optimization cost as well. All right, so my goal in this talk is not to... I've spent a little bit of time talking about this optimization problem. I just want to explain that the point is it doesn't depend on a huge number of parameters. Okay, it uses all kinds of sophisticated training, but it's of course highly non-convex. All right, that's the point. All right, so let me just show you now. Here's an optimization result that we were able to get now out of this. So after lots of hits and misses and adding this and adding that, we now finally have a system that gives reasonable results. And here you can see, now of course these are 3D surfaces that we're fitting. I'm just showing you 2D slices, but this result is actually fairly decent. And here you can see what happens when you piece together the hand tracings on all the slices of a cardiologist on a data set that we left out of the training and fitted to, and here's our automatic algorithm result. So we finally got good, answers, and as much as I would love to attribute this 100% just to all this modeling that we've done and everything else like that, there's one little piece that makes the difference between this and a miserable failure. Okay, and so it's how we do the optimization of the parameters. So again, this is very non-convex. If you try to use second-order, techniques like Newton's method, it doesn't work well. I mean, you have to initialize really, really close, and by that time, it doesn't become very automatic at that point. So you're really much stuck with gradient descent. So this was the demo I was hoping to show you, but I won't be able to hit the run button because it appears on the bottom of the screen. So I'll just show you the results at the end of the day. Here's the results using pure gradient descent, and as you can see, they're horrible. Okay, and here's the results that I showed you before, the good ones using a modification of gradient descent. So the modification was something that at the time just seemed to us like a hack. It turns out there's a nice, beautiful literature behind it. The way we were doing it was a little bit hacky, but so here's what we did. So in gradient descent, you can compute a search direction as the gradient direction every single time. You move in that direction. Now you compute a new gradient, you move in the new direction, right? That would be gradient descent. So so this momentum-based approach to gradient descent says, each new direction will be some kind of combination of the new gradient and whatever direction you moved in the previous iteration. And that way, you kind of build up momentum. If you keep getting gradients in a consistent direction, you'll accumulate momentum and you'll go in that direction. It actually speeds things up. But it also gives some robustness, because if you get stuck in a really narrow valley, gradient descent will keep bouncing you back and forth. And your overall progress along the valley, even if the valley itself is slowly descending, it's painfully slow because you're not moving in that direction. Whereas in a momentum-based method, since you're averaging, you can think of it as a temporal filter almost. If the average of that bouncing back is moving in that direction, after a few bounces, you actually start moving in that direction. All right. So, and that was what was happening to us. So what was happening to us, just to close out the application and now get into the real meat of the talk, what was happening to us is that constraint that we were adding that says that these three different surfaces, one that models them out, the left ventricle, right ventricle, and epicardium, can't overlap. What was happening is you were initializing without any overlap. And so the gradient energy was pulling them in a certain way. And then suddenly, during the optimization process, they might cross each other. Well, that would kick in a huge change in the gradient direction that would try to undo the overlap. Then as soon as the overlap was undone, now that component of the gradient went away, and whatever was causing it to overlap in the descent process kicked in again. So we were exactly bouncing across a very, very narrow valley in the energy landscape and making, little, slow progress, but it would take, hundreds of thousands of iterations to us to get a good result. And sometimes it would just be, just be completely impractical. We'd let it run all night. We'd come back the next morning. It still wasn't there. Okay. Whereas you put this little fix in, and in just a few iterations, it converged beautifully. Okay. So obviously this was important, and so we discovered that this has been around for quite a long time. We had never used it before, and it actually goes all the way back to Nesterov. Okay. So Nesterov came up with this method that he actually called accelerated gradient descent. That was a little bit more sophisticated than the way that we were doing it, so that there was a specific recursion formula for how you computed the convex combination, and in reality there was actually a little bit of an overshoot and a correction. It was structured as a two-step as opposed to a one, but the point is this has a rich history. So 2 years ago, Wibisono, Wilson, and Jordan published an article in the Transactions of the National Academy of Sciences that showed how Nesterov and all these other variations of momentum-based gradient descent that have been used so much over the years have a variational interpretation and can be and can kind of be cast in this variational setting using the Bregman divergence of some kind of a convex distance generating function. Okay, I'm not going to get into that piece of it so much because I'm not going to use that in the infinite dimensional setting. I need to stay in the tangent space, and so it's convenient not to have to talk about these types of finite jumps on a manifold. The more important point is that in the context of this kind of Bregman divergence, you could come up with a Lagrangian that and show that all of these momentum-based gradient descent techniques, including Nesterov as a special case, were simply particular discretizations of the ODE that came out as the Euler-Lagrange equation of this type of action. Of the integral of this type of Lagrangian. So let me just explain this a little bit more, okay? Since I don't want to get into the Bregman divergence part of it because I'm not going to use that piece of it, let's just go to the simple Euclidean case. So in Euclidean case, what does it look like? So what it looks like is this is the thing you're trying to optimize. So x is your set of parameters. And U is some kind of a cost function, some kind of energy you're trying to minimize. So now what's done is you take the integral of this whole thing. So now what is this? V would be the velocity. Okay, so if you imagine, if you go to the continuum case now, the continuum version of this, as you're moving in your parameter space, you're moving with a certain velocity. Okay, so that's V. So what this is nothing more than the kinetic energy. If you assume that your particle in this n-dimensional space has mass equal to 1, then you now interpret the thing that you're trying to optimize as a potential energy function. You now you include a kinetic energy. Now, if it weren't for these exponentials multiplying that, forget those for just a second. All this is the kinetic energy minus potential energy. That's the standard action from mechanics, right? So now you take the integral of that, and you compute the Euler-Lagrange equation, and you get out all the equations of motion in physics, right? You can formulate this even in constrained spaces. You can always write it like this. So what's the role of these exponentials? Okay, now the fact that they have the exponential form isn't so important. That's just how you generalize most of what's already out there in the literature. What's important is these are time-dependent multipliers, which makes this action integral now explicitly dependent on time. If it's not explicitly dependent on time, then what happens is the sum of the kinetic and the potential energy is conserved, during this procedure. Okay, it's not a gradient descent anymore. It's more like an equation of motion. If it is explicitly dependent on time, then it's not conserved, not necessarily conserved. And if you choose the right particular explicit dependence on time, you can make the sum of those monotonically decrease, and that's actually what happens in nature, right? So what happens in nature is you have friction, right? So if you set something in motion in nature, then you're converting, you're constantly going back and forth between kinetic and potential energy, but typically some of that energy dissipates. It's not that it goes away, it's just dissipating off of the in the form of friction. And so if you think now, let's go back to gradient descent now. I'll get back to this thing here a second. So if you look at the motivation from physics, actually gradient descent is not natural at all. It doesn't occur in nature, right? So if you put a ball on a hill, yeah, initially going to start rolling in the gradient direction, but it's not going to keep going in the gradient direction because as soon as it has a bit of inertia, if the gradient direction changes, it's not like it suddenly changes, right? So, and it gives a tremendous amount of robustness, right? If you take a ball to the top of a hill, even if the hill has lots of little divots in it, which would be tiny little local minimizers, you start rolling it down, it's going to sail over those. Now when it gets to the bottom of this, suppose there's a basin in a valley, right, between two hills, and you're trying to get to that, it will overshoot it, right? And then it will oscillate back and forth. That's actually a good thing. The overshoot is a good thing because that's exactly the thing that makes sure that whatever it gets stuck in has a nice wide basin of attraction, right? And that's what the little divots along the way, they don't have that property, and those series sail over this. So even though this wasn't really Nesterov's intent and the algorithm that he formulated, he was trying to speed up the optimization for the purely convex case. There's a tremendous amount of robustness that you get in this accelerated type of gradient descent, and you can see it in nature. Okay, so now how do we do this for functions? So again, the key is the variational interpretation. So we just go back up here now. And we're going to generate what I'm going to call this generalized action integral. I call it the Nesterov. Nesterov never called it this. He didn't look at it like this. Okay, I'm just calling it because it's sort of like Nesterov. So the generalized action integral. So you basically just have to formulate. You give me the thing you want to optimize. That's this U here. There needs to be a reasonable way to come up with a kinetic energy for it, and I'll show you an example. It's not that hard. And then now, the reason I'm calling this the Nesterov generalized action is these are the particular choices of time-dependent coefficients that would come out if you wanted to adapt this specifically to Nesterov's algorithm in the continuum. Okay, it doesn't have to be these. That's the combination that you get. And the point is that you now get this type of friction style equation of motion. You basically get equations of motion that you accelerate now in the gradient direction. Your velocity isn't the gradient, the acceleration is the gradient, and that's much more like what you see in nature. But the point is you have friction. So there's still a monotonic decrease in something that makes you converge. But along the way, you actually can have temporary moments where you go increasing in the thing that you're trying to optimize. So at the end of the day, you will still go to a local minimum, but you're not constrained to be monotonic in your energy. You have to be monotonic in the sum of the kinetic and the potential. So you're throwing in some dynamics into the optimization problem to kind of relax the process to get to the local minimum, but you're not in any way constraining or changing the local minimizers of the energy functional. Okay. All right. So that's the idea. Now, what happens is that you can question, well, what should the friction be? So what you would get is as you bump the friction up more and more and more and more, it slows down more quickly, right? So it can get caught in a shallower local minimum for the higher the friction is. If you go to the infinite friction limit, you get gradient descent. Okay, so that's how you would relate gradient descent to something in nature. So if you have incredibly high friction, then things are almost gradient descent. All right, so All right, so let's now do this for the sake of PDEs, and then I'll show a demo because it's really cool the way that the optimization goes a completely different path. Okay, so let's consider a class of calculus of variations problem. You have an energy functional E. It consists typically of terms that depend on your unknown as well as its gradient. Typically, these are going to be regularizers over here, and these are typically going to be terms that relate your data to some kind of a measurement, So you can write down the Euler-Lagrange equation, and out of that you can extract the gradient. Okay, and so this is a gradient, of course, in the L2 sense. Now, gradient descent would be the PDE. Now, so this gradient will typically involve spatial derivatives, right, of your functions. Your energy depends on a function. Its Euler-Lagrange equation involves spatial derivatives. So the PDE structure comes out in gradient descent by artificially adding a time derivative and just setting the time derivative of your evolving unknown equal to minus the gradient. Okay, so it still is gradient descent. It's just that what happens is that in the gradient itself, you have spatial derivatives that get mixed with the time derivatives. That's what makes it different than the finite dimensional case. Okay, so it's a PDE now, not an ODE. All right, so how would you do the accelerated version of this? Okay, so you have to make up a kinetic energy. So it's pretty natural to do so, right? So here's the energy function that we already had to begin with, okay, whose gradient has spatial derivatives. The kinetic energy is we just integrate over the domain of our function u. We assume some kind of a density, and then we just look at the pointwise derivative, and we just integrate it. That would be a very natural kinetic energy. Now, if you assume the density is constant, you can pull it outside the integral, and you're basically just integrating the time derivative squared, okay, with a factor of 1/2, so you don't get a factor of 2 when you take the Euler-Lagrange. All right, so you plug all that stuff in. That becomes the action integral. Okay, so now you're not going to do a gradient descent anymore. Now you're just going to compute the Euler-Lagrange PDE of this, and you will flow along that. Okay, and so that's what you get here, and that gives you this generic, this equation 4 at the bottom, that gives you what I'm calling the accelerated descent PDE. So if you notice, how does this differ from gradient descent? So gradient descent would be one time derivative over here equals minus the gradient. Okay? Now it's that the acceleration, two time derivatives, is equal to minus the gradient. These are just some multiplicative terms. This is the 1 over the density. You can just set the density to 1. That'll go away. This b of t is just what you choose to multiply this by. In reality, all you need to guarantee friction is this. Okay, so you can get rid of this. You can set that to 1. So these are just some scale factors. They're not that important. The important thing is that you've got that the acceleration is equal to minus the gradient, but you also have this first derivative here multiplied by a, which is a dissipation coefficient. It's like a frictional parameter. Okay, so that's the PDE. It's now a second order PDE in time rather than a first order PDE in time. All right, so let's apply that structure to a very general class of regularized inversion algorithms, and then I'll show a few examples on image processing problems that fit into this general category. So in general, if you want to do regularized inversion, not every problem fits this model, but here's one that is certainly quite general, right? So you have a set of measurements. You have an underlying model U, okay, that relates to measurements G through some kind of linear operator. Okay. Now, it's not always linear, but you can always linearize it, right? Okay, so now what you do is you want to penalize. This is basically the residual between the forward operator applied to your estimate, your actual measurements. We're going to take an absolute value, and we're going to have some kind of monotonically increasing penalty on that. Okay, of course, one example is just quadratic. Okay, then, your problem might be highly underdetermined, or there might be noise. For either one of those reasons, you might want to regularize. So in addition, you're going to pay a cost for the gradient, for high spatial gradients and variations in your estimate. So you're looking for some kind of a regularized version of an estimate that will still reasonably approximate the measurement data G. Okay, so once again, you assume that this R is a monotonic, penalty. And we also make the assumption for, well, just for existence and uniqueness, we also need that we should have that it's convex as well. Just this, the function R. Okay, the whole thing doesn't have to be convex, but R should be. And so we put that penalty on the second derivative as well. Okay, so we have this. This is very generic. All right, so now for this, what would you get if you compute the gradient of this thing? You're going to get your linear operator times its adjoint. Okay, here's your residual, and then you get this big expression here based on your assumptions that it's monotonic. That whole thing here, even though it's nonlinear, will nevertheless be positive. Okay, in a similar way, your regularizer can be broken up into two different types of terms. One would be the second derivative normal to the level sets of your function u, multiplied by something here. We assume this thing was positive. Okay, it doesn't have to be linear, but it's positive. And then we have all of the rest of these second derivatives, right? So we're breaking the Laplacian down into one component that's kind of along the level sets and one that's normal. But the point is, and you always have this decomposition no matter what. But the point is if you chose these monotonic penalties, as well as convexity in the penalizer for the regularity term, you are always going to multiply these by positive numbers. Of course, then you have these negative signs. Okay. So what does that mean? So first of all, it means that the gradient descent will be well posed, okay, under these assumptions on how you regularized. So the gradient descent now is going to flip the sign of everything, and you're going to have these two terms here are going to represent positive diffusion. Okay, so your forward diffusion. And then this is going to be, in general, some kind of a reaction term. It can sometimes be advection if there were, derivatives in your forward operator, but the well-posedness, as well as how fast you can simulate this numerically, is typically dominated by these two terms. Okay? So gradient descent for this class of energy functional usually gives rise to some kind of a reaction diffusion equation. It can be quite nonlinear. That's fine. But it's a reaction diffusion equation in most cases. All right. If you plug this into that generic equation that I showed you for the accelerated PDE, what arises is a nonlinear wave equation. So because now you're pairing these second derivative spatial operators that are positive if you put them on the right-hand side of a single time derivative is equal to that. That's a diffusion type. That's kind of a parabolic PDE. Now, if you pull them now you have two time derivatives. If you pull these to the other side, you have positive derivatives in time minus positive second derivatives in space. That's a wave equation. Okay. Now, there's also this time derivative here that comes from your friction coefficient. That's a new entity as well. But the point is, the spatial derivative terms that arose in the gradient are now being paired to the second derivative in time of the opposite side. You have a wave equation. So that completely changes the behavior of the evolution. And here's the beautiful thing from a numerical standpoint. When you discretize numerically a diffusion equation, you have to take very small time steps because in general there are stability conditions. They're called CFL conditions, right? And you have to choose the time step to be proportional to the square of the space step. So as the spatial resolution of your grid gets finer and finer, your time step has to go down very, very harshly. Okay? Whereas when you discretize a wave equation, the time step is now proportional to the space step. So that's a huge boost. So in a way that's completely different, from Nesterov's analysis, you actually still get the speed off, which is what Nesterov was after way back when he invented the method to begin with in the finite dimensional case. So you get a speed up, but the speed up shows as a huge relaxation on the time step constraint when you discretize the resultant PDE. But what I find more interesting is the nature of the PDE. It's transitioned from a diffusion type equation to a wave equation. And it gives some insight as to why this can be robust against local minimizers. So let me show you some. So let me just show you a few special cases, and let's look at some demos, and you'll see what I'm talking about. Okay. So let's just we'll do 3 examples. In reality, all 3 of the examples happen to be convex. But when I show you the demo, you'll see why even in the non-convex case, you're going to get a tremendous amount of robustness. So one is quadratic regularization, right? So in that case, I'm just going to penalize the the derivative by a square, the norm of the gradient by a square. I'll also quadratically, penalize the fidelity. And in that case, the accelerated PDE comes out to be the purely linear wave equation, in fact, which you see right down here. Okay. So these two terms here and here came from the gradient operator. That's the penalty on your regularizer. That's the penalty on your fidelity. And that's your friction coefficient right there. Okay. Another would be Beltrami regularization, where you look at this the square root of 1 plus some amplified version of the gradient. So the geometric interpretation of this regularizer is you can think of u as you can convert u into a surface just by thinking of the graph of the function u. So u is a height. Now you scale it by some beta value, and now you have a surface. And what this is, if I take the integral, if you ignore this 1 over beta outside, if I take the integral of that, that's nothing more than the surface area of the graph. Okay, of the surface that I create from the graph of u. The reason I have a 1 over beta is so that as beta goes to infinity, this doesn't blow up. As beta goes to infinity, this will go to the total variational norm in the limit, is what it'll do. Okay, so in that case, the accelerated PDE takes the form of a quasi-linear type of wave equation. Okay. And just for the sake of generality, I added the possibility that you could have a kernel. If you want to do this for de Bleuren, you're going to have some kind of a convolutional kernel that acts on your estimate before you compare it to the data. So you can throw that in there as well. Okay. Technically, that would convert this into an integral differential equation as opposed to a PDE, but it won't affect any of the stuff that I'm talking about. Okay. Then, of course, as you take beta to the limit, you can look at total variational regularization, and if you plug that in, now gradient descent has some real problems as an approach to solve the TV problem. I mean, it's known that it doesn't work well. It works quite well for the accelerated case. So in the case of the accelerated PDE, the total variational regularization has the form of this nonlinear wave equation that you see over here. Okay. All right, so let's look at some examples now. So here's an example of, this is just the quadratic regularization case. And I'm going to show you this example, not because that's a good method for denoising or simplifying an image, because it blurs things horribly, but it allows you to see in a really compelling way the difference between the behavior of the gradient descent PDE as a diffusion type equation and the accelerated descent PDE as a wave equation. Okay, so let's do the diffusion. That's technically reaction diffusion, right? Equation for gradient descent and see what happens. So I'm going to start with my initial estimate of the smoothed image being the image itself, and I'll just start running the PDE, and you see this diffusion occurring. And it takes roughly 600 steps for it to start to, kind of converge. Technically, it's converging asymptotically. It won't converge in finite time at all. But it will get down to kind of machine precision after about 60,000 iterations. Okay. Visually, after about 600, you can kind of see that it converges. Okay. Now, let's see the exact same energy functional, same parameters, same fidelity versus, and same initial condition, and I'm going to now run the accelerated PDE, and I'm going to purposely put a very small dissipation, a small friction coefficient. Okay, in reality, if I want this to converge fast, I'm going to bump it up. But I want you to see. This is really cool. I want you to see what happens, so you can see the extremely different behavior of this as a path to get to the exact same optimizer at the end of the day. Okay, so here we go. In the beginning, it almost makes everything look worse. You like it, and then now this is the same number of iterations, 600. Okay, and as you can see, I got to the same answer. In reality, I got to this answer a little bit earlier. And had I bumped up the dissipation, I would have gotten to this answer way sooner than I got to it in gradient descent. Okay, so. You want to see again? All right, let's watch this again. All right, so that's that's it. So now let me show you something more practical, which for an actual way of simplifying the image. I don't want to call this denoising. I'm just saying let's try to get a simpler representation of the image that doesn't have all the fine scale. Let's get to a coarser scale representation of the image, but that still has decent edges. Okay, so this would be gradient descent. Okay, so I'm going to run gradient descent. This is the Beltrami type of regularizer, which is an approximation of total variation without staircasing, basically. So I'm running it, and as you can see, it's changing very slowly. But eventually, you're seeing it is little by little removing fine scale features. And as a gradient descent diffusion PDE, it's doing it in a very natural fine to coarse properties, right? It's getting rid of all the fine stuff first, then the median stuff, and then, it kind of stops based on the choice that I used for my fidelity parameter, and that's where now, it's not really converged. I can run it a little bit more. You'll see some subtle additional improvements to it as I run it, but to really run it to convergence, at least at that machine level, I would have to run tens of thousands, if not hundreds of thousands of iterations. All right, now let me show you the accelerated one. Now this one I'm not going to just play around with a small diffusion. There's a way of computing an optimal diffusion coefficient by looking at the you have to look at the linear operator in the continuum and look at its eigenfunctions, and you look at the first eigenvalue, and you can define an optimal, a dissipation coefficient, because you know that the total energy is going down, and if you want to make sure that the total energy goes down in an optimal way, it's going to be based on this eigenvalue. So you can actually come up with, you don't have to guess the dissipation parameter. You can formulate it based on your regularity operator. Using that, here is the accelerated descent. All right, and you can see after about 100 iterations, it's there. And as you can see, this is actually, now you can see that the gradient descent wasn't nearly finished, okay? Here's the result I got after 600 iterations of gradient descent. You see there's still a tremendous amount of structure, okay? For that to go away would take a tremendous number of iterations, okay? So I'm not going to, torture you by making you watch how long that takes. But you can already get an idea. If I plot now, here's gradient descent. If I look at how the energy evolved, okay? Now this is just the energy I'm trying to optimize. It's not the total combined kinetic. It's just the potential energy, okay? After, you can see that, it comes down. This is the linear plasma, not kind of in a log plot or anything else like that. So I started off here. I got down, to about 13.8 after 600 iterations. If I look at the corresponding plot, starting from the same initial condition for the accelerated one, you can see how quickly it comes down. Okay, so to get to 16 point, what was it? I forgot what it was. 13.8. Okay, so to get to 13.8 here, I only needed 68 iterations compared to 600, right? So it's an order of magnitude faster, okay? But you can see I've already practically converged even to the final result shortly after, maybe about 130 iterations. I'm not changing much anymore. At least up to 6 significant figures, I'm not changing at all, okay? So it really does make a huge difference. All right. All right, so let me just talk about how you could further generalize this. In reality, I did this the other way around. I did the curves first, and then I did these functions in flat spaces later. The reason I wanted to show flat spaces a little bit more in the talk today is maybe not everybody's interested in active contours and surfaces. I know a lot of people here do big data, machine learning. Doing this on the manifold of the curves is one more level of abstraction away from trying to solve big optimization problems, over networks and things like that. So at least if we're on a flat space, we're one step closer. But there are some concepts that I haven't talked about yet in the flat space case that I'm going to talk about on the curve case that I think could be useful even in large but still finite dimensional optimization problems. So let's get to that really quickly. So how would I generalize this to curves? The basic idea is still the same, okay? I take the same, typically active contours in a variational setting are set by writing down an energy function that depends on the curve, and then formulating a gradient, and then setting the time derivative of the curve equal to minus its gradient. Okay, so but you have to form the gradient, and you're evolving by looking at vector fields on the curve, which define tangent spaces on the manifolds of curves. It's not quite as easy. You can't take finite steps. You really have to think of it as a continuous evolution that you then discretize at the end of the day in the final PDE. So, but the good news is. All of that's already done in gradient descent for you, and there's a wide class of active contour algorithms where all that code's been put together and people have their models. So how can you take what's already out there now and just accelerate it? So again, all you have to do is invent a kinetic energy for the curve, and there's a very sensible one to do. Most gradients in the space of curves are formulated in terms of a geometric version of the L2 inner product. So you look at a perturbation of the curve as a vector field on the curve, and you integrate that vector field with respect to arc length. That's what makes it geometric. And so in this type of geometricized L2 flavor inner product, the natural notion of a kinetic energy would be this here. Okay? So you assume a density per unit arc length. It doesn't matter. Okay, you say, well, wait. That means total mass isn't conserved because if the curve changes length as it evolves, masses change. It doesn't matter. It doesn't change anything about the physical intuition of the setup of the problem. Okay, we're borrowing behaviors from physics, but we're not trying to make this a physics problem. Okay, so so if it's constant, I can pull aside the outside the integral. I'm just going to integrate over the curve with respect to arc length the norm of its time derivative squared. That's my kinetic energy. Now I can formulate my action integral, which is whatever the original active contour energy was, okay, subtracted from this kinetic energy with these time-dependent multipliers that I showed you before in the generalized action, and I just crank the variational calculus machinery to come up with this Euler-Lagrange equation here. All right. So it has very similar structure to what you saw in the flat case. Here's the acceleration. Here's the second derivative of the curve. This is the gradient. Now gradient descent would be one derivative equals that. Now this is multiplied by something that depends on the density. That's not that important. Here's a frictional term. Here's the first derivative of the curve. Before I was showing this on the other side, so now you see it with the minus sign. Here's a friction term. And this thing here is what comes, this thing here you didn't have before in the flat case. This term can explain the fact that you're on a manifold, and as you're moving from one place to another, if you want to talk about dissipation, there's a certain type of transport that needs to occur. If you want to relate what's happening to one place in the manifold to the next, there's, you have to think of parallel transport. This kind of explains that for you. The beauty is you didn't have to think about that and understand how to write that down. You just computed the Euler-Lagrange equation of this action integral and you got it. But if you want to try to understand that, that's kind of what it's doing. It's showing you how the advection occurs from place to place in the manifold since you're not in a flat space anymore. If you were flat, all that would go away. Okay, so let's look at demos for the active contour case, and then I'll explain a couple ideas of what you can do. Wait. Oh, sorry. Let's go here. Here we go. And then I'll go back to a couple of slides that talks about more interesting things you can do with the mass now. Okay, so let's look at a really trivial example here, just so you can see. This is like the quadratic regularization that you really wouldn't actually use in practice, but it demonstrates the difference between gradient descent and accelerated gradient. Well, same thing here. There's no need to use an active contour to segment a binary image, but let's just see the difference between gradient descent and accelerated descent for an active contour. So here's a standard gradient descent active contour. And as soon as any piece of the contour kind of hits the edge, it kind of stops and everything else catches up and you're done. It's still evolving, but you can see that it's at a steady state. All right, let's reset. Same initial condition. I'm going to say, oh shoot, I can't reach the button on here that allows me to put the acceleration on. Let me.
Can you reduce the?
Rats.
Can't you reduce the?
I know what I can do. Let me do it manually. All right, because this is a cool demo. All right, I will just do it manually. Okay. All right. Okay, here we go. Let me turn that on. Okay. All right. So now starting from the same initial condition, if I now evolve, you see that it takes a totally different path. It overshoots, it comes back, it forms this wave, and eventually, due to the dissipation of friction, those oscillations eventually die out. So this, now I'm going to show you a non-convex optimization problem. Okay, so here's an example. Let me actually do two, so I can also show you the benefit of using level set methods, that I can do topological changes. All right, so here's an example now of gradient descent. Oh wait, no, shoot, that was, I forgot. That's the accelerated one. It doesn't, gradient descent gets stuck in me. Hold on, let me reset, let me turn off the acceleration. Let's see. Okay, all right. If I run gradient descent here, I get stuck. And it doesn't matter where I start. I'm definitely stuck. Let me start with the contour somewhere else. I'll start over here. I run. Okay, I get stuck. There we go. Now it's stuck. Okay. There's probably tens of thousands of local minimizers in here of possible contours that can get stuck. Right? They're all over the place, but they're rather shallow. But the problem is I can't exploit that shallowness in gradient descent, because even if I play tricks, let me just, even if I dilate the contour just a little bit to get off it and run it, it'll just go to the next one, to the next one, to the next one, to the next one, right? So there's no trick. But if I turn on acceleration, okay, so let's go back to that same contour. I'll put the acceleration back on now. And as you can see, it sails right over. I've bounded the number of iterations, so I need to keep doing a new number here. And as you can see, now it's done. Now, I am still responding to the noise, but I'm responding to the noise in the vicinity of a nice good minimizer. Okay, so if you wanted to smooth out some of the noise, you could add some more regularity to the energy at this point. But the point is the noise that I'm responding to is in the vicinity of a nice, deep and wide local minimizer, as opposed to the noise that's further away from the shapes that keep the minimizer very shallow. Now I want to show you something even more compelling. All right, so let me turn the acceleration back off. I'm going to run until I get into a local minimizer now. Okay. All right, so I'm in the minimizer. I'm evolving now. I'm not moving anymore. Now here's the thing. In the continuous world, if I'm in an actual local minimum, acceleration will not help me, unless I start off with some non-zero initial velocity. That's a trick you could use. You could add a stochastic element into the velocity so that you're never, so that even when you get to the minimum, you kind of stochastically float around it, okay? And in that case, even if you start at a local minimum, you could perhaps escape it. But if you don't do that, if you start in a perfect local minimum, acceleration, if you start out with a zero initial velocity, will not help you. But numerically, you don't. And to some sense, if the minimum is shallow enough, you don't even need a stochastic element, because just the behavior, the fact that at the level of the grid, you basically oscillate sub-pixel around the minimum, right? You're taking finite step sizes. There's something somewhat stochastic about that. So I am, visually it looks like that contour is stable, but if I zoomed in sub-pixel, you'll see it's basically, floating around. There is a little bit of kind of stochastic, behavior going on. Hamid might kill me for using that word stochastic, probably in a non-rigorous way, but that's enough to accelerate you out of it. So I'm going to turn on. I'm not going to change the contour now. All I'm going to do is I'm going to turn acceleration back on. Okay. Now, when I turn acceleration on, the other important point for me to tell you is that if it wasn't already on, as soon as I turn it on, it's setting the initial velocity to 0. Okay? So I'm starting in the local minimum with 0 initial velocity, and now I start to evolve. And it pulls me right out. Okay? So, of course, I have to keep doing more steps. So I'm about out of time, so I don't want to show you more slides, but let me just make one comment about one thing that might have bothered you initially about active contours, and I said, look, don't worry about it, it's not a big deal. And that was the fact that you don't have mass preservation. Okay? With a contour, if you define a density that's per unit arc length, and as the contour grows and shrinks, mass is changing. What if, for whatever, now, as you see, it didn't matter, okay? But suppose for whatever reason you wanted to conserve mass. Could you do it? Yes, absolutely. And it doesn't totally throw the whole framework out of bounds. It makes the calculus a little bit harder, but still, you don't have to change anything. All you do is you add a mass preservation constraint. Okay, you can write down a continuity constraint of local mass preservation. Right? You see this in fluid dynamics all the time. And then when you write down the action integral, right, the kinetic minus the energy, and you write down the Euler Lagrange, you just add that constraint as a Lagrange multiplier. And what you'll get out of that is a system of evolved equations, one for the mass itself and one for the contour. And they'll evolve together that ensures conservation of mass, not even just globally, but even locally. In that case, mass is no longer, density is no longer constant, it evolves. And this actually connects very strongly with the theory and the literature on optimal mass transport. Because that same continuity constraint in the form of a Lagrange multiplier and exactly the same type of action integral, but without the potential energy term, is the whole basis of the kind of the Benham-Ubernier approach to optimal mass transport. So they don't have the explicit time dependence in the action, and they don't have the potential energy. But this model of kinetic energy is exactly the one that's used. So you can imagine doing this, and here's where I think this approach, even though in machine learning you're typically dealing with finite dimensional problems, you can do this acceleration in the standard sense, you don't need this PDE, but there's still something you might think about taking out of this variational context. One is this. If you don't just treat your unknown as a unit mass particle in some large dimensional space, but you think that the mass is distributed over all of the unknowns, right? So in my case, the unknowns are the values of a function on a Cartesian grid. Okay? So there's a notion of proximity. Okay? One grid point is next to another grid point. There are problems in big data where you have this structure. It doesn't have to be a Cartesian grid. It could be a network, right? Nodes that, the unknowns, describe, things that are at different places in a network. So if there is this notion of proximity, then instead of just abstractly treating your whole vector of unknowns as a unit mass particle, why not distribute the mass over all of the locations of the unknowns? And you can play a similar game. You can have a coevolution of mass that moves from node to node as your primal variable. I mean, I don't really call it primal dual. It has nothing to do with that, but it has a similar flavor that you have two things evolving. As the thing that you're optimizing is also evolving. And what I didn't show in the slides is there are additional tricks that you can play, because in addition to defining a kinetic energy that is used only during the optimization process, you can add to the potential energy of the thing that you're trying to optimize. You can add an additional potential energy that depends only on the mass configuration, that favors a constant distribution of mass. So you imagine like you're moving a bucket of water and it's flat, and as you start to move it, waves start to occur, but then when you finally get to the minimum, it settles down again, right? this is a way of putting regularity into the optimization process without changing in any way whatsoever the local minimizer that, the class of local minimizers you can go to. And so while I need to model densities in mass in the case of contours, okay, and while it is certainly sensible to do it in the case of functions on flat spaces, you could do it, even though you really don't need to, you could do it in very high dimensional optimization problems and get some, it gives you a whole new thing to play with to try to speed up and make your optimization more robust. So that was the one thing that I wanted to mention as having applications outside the stuff that I'm talking about today. And I'll stop there.
Any question?
I can ask a question.
Sure.
So what I understood is that you're connecting optimization algorithm, which is a discrete time process, to a differential equation, which is continued through the Lagrange equation. But then the important part is the discretization of the paths if you want to go back to the optimization domain. So is there any, I suppose that you only use a uniform discretization.
There's nothing in the formulation that requires that. Okay. Now, in my experiments, yes, I used uniform grids.
So you think that it's not so important what kind of...
No, in fact, you don't even have to do it of our Cartesian. You could use finite elements, right? I mean, there's lots of different ways of discretizing, of solving continuous PDEs. I mean, the same thing applies to ODEs, right? I mean, so even the stuff that people are doing with classic Nesterov and the methods, I mean, what that paper that I talked about from Michael Jordan was about 2 years ago, what they showed was that that all of these discrete recursions that people use, at least most of them, can be described as particular discretizations of an underlying continuous ordinary differential equation. Okay, so what I've done is said, okay, well, what about the realm of PDEs? Okay, which is a little bit different, but there are some tremendous points in common, and your question, I think, is one of those things that's common between both. So yes, at the end of the day, you need to discretize, but one of the advantages of PDEs is that when it comes time to discretize, the conditions for making sure that your discretization is stable are well understood. There's a whole, I mean, and it's very different than an ODE. Sometimes they're similar, but in general, it's a different approach than what's done for ODEs. So sometimes formulating things, so a lot of things have been done heuristically in the finite dimensional case, as opposed to doing it from this variational context and instead in the discretization, just because it's sometimes tricky to make sure that the discretization is stable. In PDEs, it's usually easier, usually. So, because typically if you can linearize the PDE, you can use von Neumann analysis to come up with a CFL condition that tells you how big of a step that you can take. And then that gives you, at the end of the day, a discrete algorithm. I didn't address the discretization, so I have a paper that'll be uploaded to archive in just a couple of days, and 70% of the paper deals with the numerical, how to numerically discretize these accelerated PDEs. And you'll see there's some very generic formulas that you can use based on the structure of the gradient. And you can look at the continuum gradient, and usually people do very sensible spatial discretizations of the derivatives, and if you use most of those, then there's simple formulas that tell you how big of a time step you can take. And typically what you're going to do is you're going to take the maximum one, because you don't care about accurately simulating the process, right? That's one of those, you're not trying to simulate. PDEs in nature, sometimes you simulate them numerically. You want small time steps so you get a nice accurate. We really don't care, right? We just want to get to them. So the natural way to address how to get the discrete algorithm at the end of the day is just formulate it continuously, get the PDE. Now your space step will typically be dictated by the structure of your data, okay? And now your time step, you'll just choose the maximum stable one, and there's a simple rule to do it. And that's how you can take the arbitrariness out of how to go from continuous to discrete.
How do you envision your proposed algorithm to be modified to the case that you tracking the active changing contour, say in a video? So in the traditional communication, we have the problem of adaptive signal processing, we're tracking the time varying PAR coefficients. So we do not change the gradient descent a little bit. We do not change the gradient descent, but just works. But maybe a little bit modification to the formulation. But in your case, do you envision your algorithm will be able to track the contour evolve along the time?
Yeah, so what will happen is, if you're doing tracking, so just to make sure I've understood what you're saying, is you're saying that in the case of gradient descent for tracking, maybe this isn't what you mean, but what I think you were saying is in the case of tracking for gradient descent, as the thing you're trying to track evolves a little bit, the advantage of gradient descent is that you can just do a few iterations and correct your previous estimate.
Yes, so you actually follow those change of the coefficients, like use the traditional LMS or ILS.
Okay, so that is what you meant, and,
yes.
And you're worried that if you switch acceleration, you lose that feature.
Yes,
correct?
I see some of the bounce back and forth, so I worry a little bit if we are doing it in real time. Probably it's going to overshoot and
there were about 15 slides on contours that I skipped here just because of time. One of the things that you could, so first of all, if you still are near, so I was showing you examples where I started very far away from the minimizer, okay? That allows acceleration to accumulate, okay? And oscillations to become very, very large. Okay? Now, if I had started, you still share one property with gradient descent, which is if you start near the minimizer with zero, now the key is with zero velocity. If you start near the minimizer with zero velocity, you're still going to converge to it very, very quickly. You won't need that many steps. And the amount of overshoot, which in the case of a contour is in terms of oscillations, right, is going to be small, right? Think of dropping the marble on the hill. If I drop it far away from a local minimizer, then by the time it hits that, it skips over it, right? And in tracking, sometimes you want the local minimizer, right? Because right? Okay. So, but if I start really close to the little, if there's a little divot in the ground, and I start close, well, then it won't. Okay. So that's one thing. So you still get the benefit that if you're close, and it just moves a little bit, you don't need to kind of do a major re-optimization from scratch. You still get the benefit. Now, in terms of control of the oscillations, first of all, if you start close, the oscillations won't grow that much. So you might not need to do anything. But you can add diffusion terms. Now you're going to lose the ability to take larger time steps, but if you were using gradient descent, you were already stuck with this anyways. So if you are fine with having a time step that's dependent on a diffusion term in the flow, you can add a diffusion term not to the contour itself, but to the velocity. Okay, that will tend to diminish the size of the oscillations without in any way changing the local minimizer, right? So if you think about it, if you start with zero velocity, what causes oscillations is that one part of the curve moves a little bit faster than the other, and because they're no longer independent, because of this wave equation, that forms an oscillation. If you diffuse the speed function, okay, I'm not talking about diffusing the curve itself, which is what a regularizer would do, okay? But if you diffuse the speed function as it's going around, you can keep the size of those oscillations small, okay? And but you still get the benefit of acceleration and robustness, right? So that's something you can do. What you lose, so it seems like, well, that's too good to be true. You still get pretty much the robustness. What you've lost is the ability to take bigger time steps. But if you were doing gradient descent, you're stuck with that anyways. So for the same time step that you would have taken in gradient descent, you can get the robustness benefit, not necessarily the speed up benefit. You can get the robustness benefit of acceleration and still, have all the same benefits of gradient descent.
Thank you.
Okay, so I think time's up. And let's thank our speaker again.
Converge.